All right. So I will be building on my previous talk on Prolog. I indicated that in the meetup page, so please feel free to look at that at some point. So Mercury is a logic programming language. So let me remind you very quickly what logic programming is. It's basically a domain-specific language for a certain kind of logic puzzles. And the puzzles are of this form, that we have a universe of objects, and we have some properties of these objects that we describe. So the example I gave here is the one that I gave in my Prolog talk. So imagine that we are given this information, that all jumping creatures are green, that all small jumping creatures are Martians, and all green Martians are intelligent. And then we have facts that Turks is a small and green creature, and Pugvadurk is a jumping Martian creature. And we want to find out who is intelligent, if any. If anyone here from this universe is intelligent. So the program shown in blue is a Prolog program, complete Prolog program that can be compiled and run, which basically shows you that Prolog is a perfect domain-specific language for problem domain like this. The way that Prolog executes this program is based on the so-called horn clauses of classical logic. And I will briefly talk about this in the next slide. Prolog now is a language that's almost forgotten, but it has a legacy that still lives in SQL databases, in Datalog language, which is not very well known, I guess, but still it is not yet dead. And in various improvements in language design, such as the syntax that I've shown here, the syntax for pattern matching lists, the underscore dummy variable that we don't care about to match anything, that is all out of Prolog. Prolog was the first language that did all this. Now we take this for granted. That is the legacy of Prolog. So some people are not familiar with logic programming and Prolog, so that's just a very small amount of information here about it. So in Prolog style logic programming, we have capitalized symbols that are variables and lowercase symbols that are not variables. They're constants or predicates. And if you look at the example of the clauses written here, so green x is proved if jumping x is proved. And in the logic, it can be written like this. So if for all x, jumping of x implies green of x. So jumping of x is a predicate, green of x is another predicate, and the predicates hold or don't hold on certain objects or values. Another example of logic programming is this rule: path of AB holds when path of AC holds and path of CB holds. So this is a program that is translated into logic like this. So for all AB, there exists a C such that if there exists a C such that path of AC and path of CB both hold, then path of AB holds. Now, the quantifiers are not written in this program. As you can see, they're implied. So when there is a variable on the left that is free, then it is universally quantified. And when there is a variable on the right that is free, then it's existentially quantified. And that is implicit. And the query looks like this, and it means we want to prove that there exists an x. So you see x is on the right. So it's implicitly existentially quantified. We want to prove that there exists an x so that the predicate intelligent of x holds. In order to find that proof, we only need to find an x for which this predicate holds, and the runtime engine will perform a backtracking search over all the rules and predicates that were given to find what possibly this proof. And logical variables are assigned or unassigned as needed. So, for example, to run this, so I remind you that this is a complete Prolog program. There's nothing else that you need. The runtime engine runs this by looking for any way to prove that there is an x for which intelligent of x holds. There is one rule which says intelligent of x holds if green of x holds and Martian of x holds. So now we need to prove two things, that there is an x with green of x and there's an x with Martian, the same x, which is also Martian. Now these are called goals. So this is a goal that we're going to prove. We have reduced it to two other goals. Now we need to prove both of them. So how do we prove green? Well, we'll look at the facts. We have a green, Turks. That's obviously green. So x is equal to Turks. And now we continue. The second goal is Martian of Turks, but we cannot prove that. There is no fact about that, and Martian of Turks can be proved if we have small Turks and jumping Turks. Well, we have small Turks, but we don't have a jumping Turks, so it's not jumping. So we fail to prove that Turks is a Martian, and so we fail and go back to here, try to prove green in a different way. So now x is unassigned. X was equal to Turks just a second ago. Now, since we failed here, we go back, x is again unassigned. We are looking for other ways of proving green. Now here's a green x when jumping x. Well, let's look at jumping. We have a jumping Pugvadirk. So let's see, x equal to Pugvadirk. Martian Pugvadirk. Yes, Martian is Pugvadirk. It's all done. So now x is Pugvadirk, and we have proved that there exists an x such that intelligent of x holds. So that's how the runtime engine interprets a program like this. The programmer only needs to supply this text and compile it. So let me then go to Mercury. It's basically a Prolog dialect, you could say. It's very similar. It has logical variables, predicates, rules in the same syntax and almost the same semantics. However, it also has functions. So now let me remind you, for those of you who don't know about Prolog, and by the way, how many of you have never seen Prolog ever in your life? Okay, good. So in Prolog, there aren't any functions. There aren't any values that you can just compute. Only predicates. In Mercury, this is not so. There are functions as a primitive. There are higher order functions and higher order predicates, which I will briefly demonstrate. There are some data structures that are not typical of a Prolog environment, such as an array, hash map. There are very interesting things that are called modes in Mercury, which I will explain, which will basically determine what predicates do. What does it have? Does it require something to be defined before you can run it, or will it find some values on its own, and so on. So Mercury has polymorphic types. It has type classes, similar to Haskell but limited. It has universal and existential type quantifiers, which are, again, limited, and I'm not sure that they're very useful, but they're somehow supported and make things sometimes harder. There is an interesting thing that predicates are analyzed for their termination and determinism. So a Mercury program knows that a predicate is deterministic, that is, for example, will always find a solution, or that it will not always find a solution, or that it will find many solutions. It knows this. It's an explicit annotation on predicates, which is called determinism. So multi-threading, parallel codes running, and exceptions. There are another features that this language has. And finally, a very important point is that the language is compiled. It is not interpreted. It is compiled to a variety of backends, including .NET, Erlang, and Java, and 2 different C backends for low-level code and high-level code, which is basically trying to... So this language is not compiled directly to any virtual machine right now. It's compiled to source, C, Java, and so on, and then compiled further using the other toolchain. And one of the goals of this is that the language has type-level compatibility with all these environments. So if you want, for example, to have part of your program written in Mercury, but everything else is in .NET, then you select a compilation option to .NET, and then you get a .NET assembly out of it. If your main product is in Java or JVM language, you select the compilation option for Mercury to compile to Java, and the types will be compatible with Java. So let me show you actually. Let's see. Let me show you the Martian's code, perhaps. So this is the Martian's code in Mercury. There is some boilerplate in the beginning. Now we can define a type for Martian, which is a union type with 2 values, and then we write more or less the same text as we had for Prolog, except that now this is statically typed. And in Prolog, these were just symbols with 1 common type. Now this is of type Martian. Small and green and so on are predicates that know that they're only applicable to a Martian. This is type. So type is inferred and enforced. Yes.
So is Martian, there's 2 versions of Martian there? Are they in different namespaces? Or?
No. So this is just a union type. This is like a discriminated union. So
the constant Martian is a value.
The constant Martian is a type name.
And then there's Martian that's used as a predicate.
No, it's not. Actually, that's what you're asking for. Yes. There are different namespaces. Sorry, I didn't understand the question. Okay. So yes, the Martian, the type name Martian, cannot occur in the predicate position. And so yes, they're completely different namespaces. So I did reuse Martian.
Because you could imagine that Martian as a type name, as a predicate, would be the things.
Yes, you could imagine that kind of implementation, but that's not happening here. Okay. So this.
Can the constructors take any values?
Yes, I will show later. This is just ordinary algebraic data types. So in this case, I don't need any values. I just need 2 names, but basically, yes, it's a full algebraic data type system. Now there is a bit of a mess under the main function, and this mess is the input-output. So can you read this? Should I make it bigger?
It's fine.
It's fine.
Okay, thank you. So the thing is now, in order to write anything in Mercury, to output or read anything, you need this input-output library, which requires you to thread the state of the world through each function. So the IO, the exclamation mark IO syntax is a shorthand for the world values, which are threaded through all these functions. So this is the older way, I guess, to make input-output before the monadic became fashionable, where you have basically the old value of the world and the new value of the world, which are hidden in this IO, the exclamation mark IO syntax. There are two values there, and they're threaded automatically by the compiler if you write things like this. However, it also means that your main predicate cannot backtrack, because you cannot undo the changes to the state of the world. And so it must be that that when you write something, so you cannot just write x. So yes, you computed x over here, but this thing could fail to yield any solutions, or it could yield more than one solution. And the compiler cannot check this at compile time. So the compiler requires you to provide for the case that there is no solution. So that's why you say if intelligent x. So if this goal succeeds, then you have x, and then you can write it to the screen. But otherwise, you don't have x. So then you can write an error message if you want, but you cannot use x in there. So let me return to my slides. So I showed you that input-output is a bit unusual. There are other things that Mercury adds, and there are types, modes, and determinism. So each predicate has a notation, which is what type it is. So here's an example. The main predicate has an annotation. You have to declare it like this. So it has a type. It takes two arguments. One argument is of type IO and mode DI. Now DI means destructive input. The second argument is of type IO and mode UO, which means unique output. So what does it mean? Yeah, and here is CC multi means committed choice multi-valued. So this is some strange thing that they invented in order to make things somehow more deterministic. So first, what is this destructive in and unique out? This means that the first argument has to be given to the main predicate, but after the main predicate evaluates, the first argument will not be available. It will be destroyed. The second argument is a unique output, which means that it will be created by the main predicate. So the first argument is the previous state of the world, and the second argument is the next state of the world. The next state will be created, so it's an output argument, but it's a unique output. It can be created and only used once. Once it's used, it cannot be copied. So the states of the world will be then forced by the checking of these modes to be unique. So basically, this is a shorthand for two arguments. So first argument, second argument. Then you have here first argument, second argument, and first argument, second argument. So basically, you can concatenate input-output operations, and they will thread the states of the world through them. And each one will be unique, destroyed, and so on. So that is how they handle input-output.
So each one of those bang IOs is a pair.
Is a pair.
Is
Yes.
actually a pair.
Yes, but it's extremely tedious to write it down, because you have to think about which pair it is. So world 1, word 2, word 2, word 3, world 3, word 4, every time. So the compiler will take care of this. Determinism. So there are lots of different modes of determinism. For example, this means there's only one solution. This means there might be one solution, there might be none. This means one or more. This means 0 or more. This means no solutions. This means one or more solutions, but we will only get the first one. will commit to the first choice. And this means 0 or more solutions, and whatever we find will commit to it. So these things are there, and the modes in, out, destructive in, unique out are predefined, but actually modes are user-defined. All of them are user-defined. There is a special sub-language to define modes. So for example, mode out means that before the goal is evaluated, the argument is free, which is not bound. After it's evaluated, it's ground, which means it's bound. And this means unique output. So before the goal it was free, and after the goal it is unique. So there's a special mode for unique values. So this is a little like linear types, like unique types. That means a value can only be referenced in one more place in your code, and it cannot be referenced in more than one place. It's created and then referenced once, and that's what you're allowed to do. And referencing it twice would mean you copy the state of the world, and then you change one of these copies, but you don't change the other. And that's impossible. So that's the way they deal with input-output. So the mode system. Sorry, do you have a question?
But okay, but you had like an if then else,
Yeah.
and so each branch only counts once.
Yes.
In terms of
Yes.
okay.
Yes. So that is why you need to use the if then else. So let me return to the main point here. Every predicate must have a type, mode for each argument. So type for each argument, a mode for each argument, which describes what will happen to the variable before and after this predicate is run, and determinism annotation, which will describe somehow how many times this thing will be run, or what is the result, what do you expect. So CC multi means it's committed choice, multi-valued. So there will be a value, at least one, and once we find it, we will commit to it. We'll never backtrack. And it's up to you to ensure this, and the compiler will check that this is so. So if you try to backtrack into this, there will be a compiler error. Functional programming. So far we've been just enhancing the logic programming with types. Functional programming means we have actual functions. So as an example, I will implement the factorial function on the integers as a predicate and as a function. As a predicate, it's a little unwieldy, as we all know if we've seen this once in Prolog, because you are proving the existence of a number f such that f is equal to n factorial. So you're not actually computing anything, you're proving existence, right? And so this is what you have to do. You make this recursion, you say that there is another variable a, which is equal to the factorial of n minus 1, and then f just happens to be equal to a times n by some miracle. And the runtime system needs to figure it out. That's what you do in the Prolog fashion. Now, as a function, you have another way of doing exactly the same thing. You write the type first. The type is written using this syntax. This is a function type, integer to integer. And then you define it as an expression. So this looks like an expression. It looks like perfectly a familiar functional code. However, if you actually run it and compile it, which I have done, you will see that the generated code is the same in both cases. So why is it the same? Well, you look at the predicate annotation. It says that the first argument has integer type and is an in mode. The second argument is integer type as an out mode. And the predicate is deterministic. So it means there's no need to backtrack into it. It will always give you the same output, and the input is required and the output is guaranteed. So that's basically a function that takes in, does something, computes something, and gives you that result as an out. So functions are actually predicates that have this determinism and mode annotation. Or you can also say predicates are functions with particular annotation. You don't know in this language because the code generated is actually the same. So predicates and functions are kind of the same thing. Another interesting observation here is that the order of goals is relevant in your code. The compiler, so you could write a factorial predicate like this or like this. So you could interchange these two goals. The code is the compiled code will be the same because the compiler will look at the annotation and it will reorder the goals so that the computation proceeds according to the mode. So the compiler knows that this predicate needs an input and gives you an output. So if you write code like this, the compiler knows that the predicate needs this input, gives you the output. So this has to be computed first, and then this can be computed. The compiler will infer all of this. Right. So another thing is that compiler will require you to follow what you say. So if you say that this is deterministic and then you write something like this, that won't compile. Because this doesn't look deterministic. It looks like there are two versions of this thing. There are two possible clauses, and that's not allowed. That's not deterministic. The compiler cannot find out whether n is 1 or not 1 here. It's not clear from the code, right? So n could be 1, and so in principle this is something that you would consider as non-deterministic. So that would not compile. And the error message says it inferred the multi-determinism, but declared det. So it inferred that this predicate has a multi-valued output. And similarly, if you define a function by clauses, so you cannot define a function like this either. It was my first mistake. I was trying to write functions like you do in functional programming. Factorial of 1 is 1, factorial of n is something. That fails because it's not deterministic. It cannot determine at compile time that there will be only one solution. Let me show you perhaps the factorial. Yes, good. Now I have a little more space. So what did I do with the factorial? I basically did what I showed you on the slides. I had a factorial predicate and a factorial function, and I print the results of applying the factorial function to a list of numbers from 1 to 6. Now, this code looks a bit strange, right? First, I need to define the test data. To define it, I need a predicate. Right? I cannot just say, let x equal this. There's no x in logic programming. They're predicates. So I cannot define a value by name. I have to define a predicate that will satisfy this value when used. All right. And, well, at least I don't have to say it's deterministic. It knows it's deterministic. Okay, so test data is this. So this is then used. There's a map function in the library that applies the predicate to a list and assigns the results to a variable. Then I write that variable. Similarly, there's a function in the library, also called map, that, so functions can be overloaded with predicates, which applies the function to the test data and writes the result. So I compiled it, and let's see. Let's see if that runs. All right, so making Java class file. You see it makes actually factorial.java. It makes let me try it again. Oh, it's compiled. All right, try again. Oops. Okay, it's compiled. Yes, I cannot. Okay, I can show you in this way anyway. So you see, it actually made some file, some Java file. It compiled it. It made a Java jar, and then you can run this jar. And the result of running this jar is this output. So let's see how big that jar is. Very small. Right. Now there's a runtime in some other jars that you need, but basically the compiled code size is quite small. All right. So an interesting fact about their solution is that they actually do have higher order predicates, but they're kind of cumbersome. So all this syntax is quite cumbersome. So here's what their solution is. We want to have functions on par with predicates, right? Predicates look like something, colon dash, goal, goal, goal. Now, a function is a predicate that says, when you compute this, you get a result. So let's imagine that this is actually a predicate, which is just written in a funny syntax, right? So imagine this is one predicate with arguments arg1, arg2, and so on, result. But it's written in this syntax. Other than this, it's a predicate, and it has types, it has determinism and modes, and so on. It's just written in the syntax, and then it is conventionally called a function. So that's what they decided to do. And that's what determines the syntax then. The syntax is always like this. So you have, for example, this is a lambda expression in their syntax. So F3 and F4 is exactly the same. Well, this is an eta equivalent. So lambda is lambda n dot factorial of n. So you see, so there's a lambda expression. Similarly, there's a lambda predicate. So this is a predicate which is anonymous and inline. So this is what you need for higher order programming. But the syntax is a bit hairy. So they do have lambda expressions. They do have higher order predicates like a map predicate, which will apply factorial to this list and unify the result with this list. And instead of putting here the name of the predicate, you could put in this entire lambda expression, or you could even define the entire factorial predicate in the lambda expression. So this is quite similar to ordinary functional programming, where you have higher order functions, and arguments of these functions or values returned from these functions can be themselves functions defined as anonymous lambda expressions. So in Mercury, therefore, you have anonymous lambda expressions for predicates and for functions. But the syntax is a bit hairy, and declaring modes for them is really quite verbose. You have to declare modes for each argument of each function that you have, and the determinism for each predicate that you take as an argument. And if that predicate takes another one as an argument, good luck. You just keep writing a very complicated type expression. But it can be done. So they have solved this. Algebraic types. So we have primitive types. This is exactly like all the currently favorite languages. Haskell, Scala, F#, OCaml, Swift, they all have the same type system at the base. Whereas you have the primitive types, you have tuples and unions, you have recursively defined types, you have types parameterized by type variable. So here's, for example, a type for list. This is a type for tree. This is a type that has some constructors, constructor without arguments, constructor with one string arguments, constructor with more complicated arguments, two arguments with a tuple of integer, and a string. So this could be, for example, point coordinates and the point label. So anyway, you can do anything that you do in the usual programming languages with algebraic meetings.
So the words like point, okay, and failed, those are like your constructor names.
Yeah.
Those are
Yeah.
special and defined.
Yes, there's special constructor names that have nothing to do with predicates or functions. So you can define predicates through them by pattern matching, for example. If something equals that, then this. If something equals, or you can just write clauses without if. Pattern matching is very similar on these types. You can have records with names and accessors, and basically that's
And you can overuse the constructor. You can reuse
Yeah.
constructor names.
yes, you can use. So you can have, for example, here's list is a type, and this is a type, but you could have a function called list as well.
Right, I meant like you could have another type with point as the constructor.
You could not, I believe. No. You could not have another type with point as a constructor, and you could not have another record with the same name either. Yeah, this is similar to the restrictions that OCaml has. It is solved by the module system, so you can define these things in different modules. Then you can have, for example, module A dot name and module B dot name, and there will be different record names. But once you import these modules, then you can say name.
That was fixed in the recent version of OCaml, the field issue.
Yes, but I think it was fixed in a cosmetic way, isn't it?
No, I think it was
Underneath it's a module name that is inserted in there.
Yeah, I think that you have to qualify it once
Yes.
for one field and then all the others. Are
Okay. Yes, that's true. I remember seeing that. However, so here, yes. So you cannot have coincident names. So another interesting thing is that a predicate could have different modes at the same time. So here's perhaps an interesting example. Let's define a unary integer representation, which would be a type like this, so as usual. We want to convert between this and native integer. So how would we convert? Well, in the usual way, we recurse. There is a first case. So we define a predicate which has two arguments, c and n. So c is this representation, and n is the native representation. So either c is equal to z, and then n is 0, or c is equal to a successor of some other b. Then b is a representation of m, and n is equal to m plus 1. So that is our definition. And now we declare two different modes for this predicate. We declare one mode where it's in-out, and the other one where it's out-in. You see, it has the same types in both cases, so we only declare the types once. And now we declare mode twice. And the result is that you can use the same code to unify given unary integer with native, or given native with unary. The same code, there's no change, no reordering needs to be done in your code. The compiler will reorder.
How does it? So somehow it's inverting that m plus 1.
Yep.
How does it do that?
So what it does, first of all, it generates two different functions for this thing. One function will be for the first mode, and the other is for the other mode. These two functions will be completely different code, actually compiled. this code will be inferred from this definition. So looking at this definition, for example, if n is given, then this is actually the choice statement and not this. It will reorder so that this is the choice statement. And then when this is given, then it knows that m needs to be inferred. It needs to be computed. So the plus predicate also has two modes. And it could give you an output if you know the two values, or it can give you one of those if you know the two others. The plus predicate has three modes. So it will be rewritten according to what you need. So what you need here is first you need to do this, then you get m, then you need to do this to get b, and then you need to construct s of b and unify that with c. The compiler knows that each predicate has specific modes. It will find the modes that fit here, together with the right types, and it will also infer the determinism. So it will tell you, actually, this is deterministic and this is multivalent. And that, of course, here is a very simple example. I don't want to say that this is a great thing to use in your ordinary life. Let me run this, perhaps. Sorry? Yeah, I'll get to that. So it made some Java file, compiled and made a jar, and then this is, so there are two tests here in this file. No, it's a test that, the first test is to unify the successor of z with r. And the second test is to unify c with 3. So you see, that is what happens. So the first one is 2 and the second one is 3. So no, this is what I wrote in here. So you want to unify this with n or unify c with 3, and that is the test that I'm running. Right, so why is it that the second one is multivalued, which you think it shouldn't be multivalued, right? Because the native integers are not an inductive type, and we don't know what they do. They're mysterious, they're opaque. When we run the first mode, C is given. C is an inductive type, and we pattern match on it. So we know that it's exhaustive, and therefore we know it's deterministic. When we run the second mode, we don't pattern match on an integer. We check conditions on an integer at runtime. We don't know if these conditions are exhaustive, and they're actually not exhaustive. And so we don't know if these conditions can be matched multiple times, maybe both of them can be true at the same time. We don't know that. So this works because of the particular simple case that it works. But basically, this code is obviously wrong. I mean, give it -1, it will just go into infinite loop, right? So it tells you that this code is not checked for determinism at compile time. It cannot infer that your thing is exhaustively pattern matched. But only for the second mode. For the first mode, it does. So, as I said, all predicates are functions, and all functions are predicates in this language. It's an interesting look at how to unify logic programming and functional programming. So, each mode, I said this already, each mode will generate another instance of the code in the Java file. If you look at the Java file, maybe it's instructive. Let's look at that file. All right, so it gets you some stuff to do input-output. It gets you some other stuff, and then Okay, what is this? Yeah, all right. So there's this class which it creates, and then there are other things, and there this is basically this unary encoding and z and so on, and then you have some code that does something. So obviously this is not something you want to edit, but the factorial code was less hairy, but still was quite unreadable. But the factorial code at least was obviously the same for the two cases of function and predicate. I don't want to make an impression that I understand what that code does. Okay. Type classes. Now, unfortunately, I was very excited initially about this. I read that it has type classes. Now we have actual Haskell in Prolog. No. Type classes are there, but they're very limited. I will show how, but okay, so first of all, yes, you have type class. You can define, for example, showable type T when there's a predicate show, which has an input-output, annotation, everything. It's just, then you declare that integer is of showable type class. And you say that the show predicate is actually this write int built-in library function. And list of T is showable if T is showable, and show list you can define recursively because you know that T is showable, and you can use show on T, and you just do whatever you want to show your list, to make it into a string and print it. The methods of a type class are unique, resolved at compile time. It's very similar to Haskell. However, you cannot define a functor or monad or anything like that, unfortunately, because you cannot parameterize a type class by a type constructor. If you look at what is available, you can say type class showable, and then there must be a variable, and there can't be anything except a variable. And when you do instance, you cannot put a T in there. It must be a list of T. So you cannot parameterize by list itself. You cannot say I'm showing any container or anything like this. So I was trying to write a code for a functor type class, and I failed. It never compiled. Whatever I tried, never compiled. And so what I tried was, for example, something like this. You can have many parameters in a type class. And then I would say, maybe I need A, B, and f of A and f of B as parameters. And then I could declare it like this. But that's not a functor. I cannot declare an instance, for example, for list. I cannot do this. This is not allowed by the syntax, and it's just a limited system. It cannot do. So, for example, what Scala does when you have a higher kind type constructor, which you explicitly denote. In Haskell, you don't explicitly denote it, but you can have higher kind type constructor. You cannot have it here. So this type class system is quite limited. Going through the reference manual and the library manual, the word monad was not found. The word functor was found in a very different meaning, because functor is a Prolog term that they used back then to denote predicate names. So, unfortunately, all right, what are other limitations? Records are not row polymorphic. Well, okay, we have some record accessors that are provided. Another thing which is missing in Mercury but present in Prolog is partial instantiation. For example, difference lists. Now, difference lists are a very interesting mechanism, but Mercury provides other data types. It provides arrays, it provides mutable arrays even. So in principle, you can argue that it's all right. But of course, The reason that they don't have partial instantiated values is that it's very difficult to describe the modes for them. Is something free when it has partially instantiated term? Is it still free, or is it partially not? How much of it will be made non-free after the goal is run? That is very difficult to describe, and they didn't do it. An example of a partially instantiated value would be a tuple where the first element is a number and the second is a variable that hasn't yet been instantiated. And you can match this with something else later, and you can match this variable with, let's say, a tree, where some parts are already instantiated, but others aren't, and so on. You can have as much complication as you want, and unfortunately, they haven't yet figured out. I mean, the group that develops Mercury, I believe, is just one research group at the University of New South Wales, and they only have so many PhD students per year that can work on this, and so they haven't figured it out. There is also no cut operator. So the Prolog has cut operator that stops the search at some point. Determinism here needs to be controlled using different means. You do if then else, you have an explicit failure, you have negation as failure, but you don't have cut. And there is no interactivity, so there's only compilation, there's no REPL. Okay, let me see. I think I showed basically all the code that I have. Type classes is a failure. It did not work. I hoped for it, but I couldn't make it work. All right. So I hope I showed you how Mercury unites logic programming and functional programming. So you can think of Mercury as basically Prolog with modes and types, and functions and predicates are kind of the same thing. They have a very interesting point of view where functions can be seen as predicates or predicates can be seen as functions according to what you want. I will put the slides up and the link is there. Thank you very much.
So, in your opinion, is Mercury a good idea or a bad idea?
Now, it's so okay. So I would say, if you want to have a solution that does backtracking for some problem, where backtracking is the most natural and obvious way of solving your problem, where no other thing such as making an iterator and filtering it and so on will give you what you want. That backtracking is really the right thing to do, so that you really want logic programming first. Then you might want to do this because it will integrate into the rest of your system. It can compile to C, it can compile to Java, it can compile to .NET, it can compile to Erlang. It can fit into your system in this way. So maybe there will be a use case for this. Other than this, it would be probably easier to take your good old Haskell and write a little logic programming library in it, or take one and use that. Maybe it will be more cumbersome. Maybe performance will be less stellar. I don't know. But this seems to be a Prolog dialect. It has static types. Nowadays, all languages have static types, and the only thing that I see as value here is this backtracking engine. It has, by the way, parallel goal instantiation, so you can do parallel, multi-threaded things. If this is somehow useful, I would say it has some merit. Other than this, I'm not sure. I mean, this. I would just use Prolog if I wanted to do scripting, because it's scripting. You want to do scripting. You don't want to think about why is this not deterministic, and this strange error message about the type that is not quite right, and I can't read that, and why, and so on. How do I make it deterministic? Okay, I mean, all that is a research project. Yes.
Can it do any indexing on the word?
Indexing on the
facts?
predicates.
Yes.
Oh yes. So it is trying to be very efficient in there. So it indexes on it indexes at least on the first 2 or 3 arguments of predicates. It does very efficient indexing on inductive data types. It tries to be very efficient there. It has tabling extensions. It tries to be an very efficient, high-performance Prolog.
Okay.
So types, all this inference of liveness and instantiatedness and so on, it's a big deal. So basically, a lot of the code is just functional after it's compiled. Just a function that compiles, computes the result, sets the variables to instantiate it, and goes on. There's so yes, so it does do it. So that's why I'm saying the performance could actually be good if you use this for a problem that is properly a problem of backtracking search.
It's been a long time since I've written Prolog, maybe 20 years or something. But I remember using a lot of cuts.
Right.
And maybe it was just for efficiency. It seemed like sometimes I needed it to keep things from going into infinite loops.
That's
and
right.
things like that.
Yes.
So the fact that this doesn't have cuts, do you think, is that a problem, or is it solved because of these modes? Or
It is not easy for me to say that because I don't have a lot of experience writing Prolog code with cuts. I understand in principle what it should be, but I haven't done it. Now, what is happening here is that every predicate must have a set of modes that are determined at compile time, and determinism, which is computed and inferred or specified at compile time. Which means that it's much easier to avoid infinite loops and infinite backtracking, because in many cases it just won't compile. You say you want this thing, it will give you a solution, and it infers that it won't give you a solution. So you need to rewrite it until it compiles. Certainly you can do an infinite loop, but I believe that determinism is controlled maybe in a more explicit way than just by putting cuts somewhere in your goals. It just says this must be deterministic.
can you remind me what the CC things are?
Yeah.
Maybe those have the effect of cuts.
So those CC is committed choice. So it means that you guarantee that your code will not backtrack into certain parts. Those parts are backtrackable in principle, but you won't do it.
Well, so the committed choice is sort of, in some sense, wrapping this code with a cut at the bottom, it sounds like, maybe.
Except that you have to guarantee that your code won't go back. So I believe that it is not an annotation. It is not a cut annotation. It's an annotation that your code is such that it won't backtrack into this. And if it will, the compiler will notice. It won't compile. So you have to put an if statement somewhere and stop your search yourself. I mean, you could probably implement cut in some way. I haven't really tried. But my impression is that they want you to go away from this thinking about cuts. They want you to think about determinism in a different way.
Right. I believe you could always get the effect of a cut with a condition and possibly some conjunctions and disjunctions. I mean, a sort of crazy thing in that's completely bizarre to me. And so, if I were writing a logic programming language, which I will demonstrate that I am, I would think in terms of conditions. And not
All right.
So, can we take a break?
Yeah. Yes, well, I need to somehow get the projector to talk to my laptop. Let me take a few minutes.
Let's see what happens. I might have screwed it up.